And these are the two formulas. We did one example using this formula last time, and today we're going to do an example in which we're going to use this formula this time. All right. So we're given a vector valued function. So that's the last page in the handout. They're asking us to find the tangential and the normal components of the acceleration. Notice they're only asking us to find the components. Well, for the tangential, we need the tangential itself, but we don't need the normal component itself. Otherwise, it's going to be a hell of a problem, right? So let's get started with number one, finding the tangential, which in this case is we need the derivative of the vector valued function. That's r prime. That's 2ti plus 3t or 6t in the direction of j plus 3t squared in the direction of k. Okay? And in order to get the tangential vector, we need to find as well the magnitude of this velocity vector, or this r vector. So let's find. That's 2t squared plus 6t squared plus 3t squared quantity squared. And so this will be the square root of, that's 4t squared plus 36 t squared plus 9 t to the fourth. And that adds up to 36 plus 4, that's a 40 t squared plus 9 t to the fourth power. Okay, and over here we can leave it like this. It's fine. Let's just leave it like this. Oh, also we need the acceleration vector, because this will be using the formula that we will use for the component that we want. So that's the acceleration vector, which is again the second derivative of the position vector. I'm going to denote both just so you can see where is this coming from. And that's going to be 2i plus 6j plus 6tk. Okay, and later I'm going to switch to component form. It's going to be better. Later on, we will also need to find the magnitude of this acceleration vector. So we'd better get everything since the beginning and then just put everything together whenever required. So that's the square root of 2 squared plus 6 squared plus 6t quantity squared. And this will give us 4 plus 36 plus 36 t squared, which is square root of 40 plus 36 t squared. Okay, so let's see. So to find the tangential component of the acceleration, okay, let me go back a couple of pages. So we need to multiply the acceleration vector, which we already did, times the tangential. Well, the tangential is not that crazy to compute, all right? It's just the derivative of the vector divided by its magnitude. And the crazy one is the normal vector, and no, we're not going to do the normal vector. So lucky for us, again, we have alternatives for the normal component of the acceleration. In this case, without going with the tangential, we found it because we need it for the other component. And in this case, all we do is the square of the acceleration vector and the square of the tangential component, which is the one that we will calculate first. Okay? So let's see. Number one, the tangential. The tangential, it's going to be oh, actually the prime one, prime. Yes, here's the thing, this is like a lot of symbols, and so the derivative, I'm gonna go to component form this time. I know there's a I, J, and K, they look cool, but to make it look more compact, I'm gonna go to component form. That's a 2t, 6t, and 3t squared. Divided by the square root of 40 t squared plus 9 t to the fourth. And well, no need to distribute for every component, don't worry, so things will go pretty nice from here. Okay, so now the tangential component this will be number one, a subscript t equals, in this case, the acceleration vector that we got before dotted with the tangential. Okay, so let's just put this in the formula. This will be the acceleration vector which we got here. I'm going to use component form again. That's 2, 6, and 6t. Dotted with the tangential, which is the one that we just did in the previous step. That's 2t, 6t, 3t squared. The whole thing divided by the square root of 40 t squared plus 9 t to the fourth. So to simplify this, let's perform the dot product here. We do component by component, and in the end we add up whatever like terms we have. However, recall that the dot product is going to output a scalar, not another vector. So let's see. So that's 2 times 2t, that's 4t. And 6 times, plus 6 times 6t, isn't that a 36t? And 6t times 3t squared, that's 18t cubed. The whole thing divided by 40t squared plus 9t to the fourth. And let's simplify in some of the like terms then. In fact, we have some over here. Let me make some space here to make it look nicer. Yes. So this will be 4t plus 36t. That's going to give us a 40t plus 18t cubed divided by the square root of 40t squared plus 9t to the fourth. Alright, so that's one. That's a sub t. That's the first part of the answer. Now let's get the other component, the normal component. And for the normal component, that's going to be, well, essentially a sub n equals to the acceleration vector dotted with the normal vector. But again, we're not going to find the normal vector because that's going to take at least a whole lecture to do. So instead, okay, let me cross it out. We're going to use the alternative formula instead. And that's a sub n equals the square root of the magnitude of the acceleration vector squared minus the tangential component of the acceleration quantity squared. And this quantity is The a sub t, the one that we just got over
Why
here.
is it minus, why is it minus versus plus?
Is it a plus? Did I do a plus? Let me check. I think it's a typo on the PDF file.
It should be minus.
So it should be minus. Yes. Otherwise, unless I did it on the no, I got it as a minus actually for the whole problem. So it's a so you might want to correct this part. This should be minus. Minus. Okay. So let's see. We have the magnitude of the acceleration vector. Didn't we get that? Where is it? Right here. So let me highlight so you can. So acceleration. That's going to be here, but we're going to square it. So a sub n equals the square root of the square root of 40 plus 36 t squared, quantity squared. The good thing is that radical would get canceled with the square, all right? Plus or minus the tangential component of the acceleration, which is this whole madness here we just found in the previous step. So, oh my God, 40t plus 18t cubed over the square root of 40t squared plus 9t to the fourth, quantity squared. Okay. Let's see. So number one, this radical will disappear with this power 2. And so this radical right here, but of course we need to square the numerator. Okay, so what are we going to get? So a sub n equals the square root of 40t, or just 40, plus 36 t squared. Okay, I'm going to leave a space here for a second. You'll see why. This quantity 40t plus 18t cubed squared, and well, because we canceled this radical with the power 2 from the formula, that just becomes 40t squared plus 9t to the fourth. So that's under the radical. And let's see. Okay, so to combine these fractions together, and in fact this will reduce really nice-ish. So let's combine like terms. So let's have an invisible one, and let's multiply numerator and denominator of the first term by the missing factor, so we can combine the fractions together. That'll be in this case this denominator. So multiply by 40t squared plus 9t to the fourth and same in the denominator. So in the numerator, okay, so let's write this as a single fraction. First of all, this will be the square root, and we're going to multiply 40 plus 36 t squared times 40t squared plus 9t to the fourth. Oh my God, I'm not gonna have enough space. This is supposed to be minus, and okay, now I'm gonna make it. Over here, and minus 40t plus 18t cubed quantity squared. The whole thing divided by 40t squared plus 9t to the fourth. And let's simplify the numerator of the quantity inside of the radical. So let's do the foiling here. Let's do 40 times 40t and 40 times 9t to the fourth. So that's going to be equal to the square root of 40 times 40, isn't that 1600? 1600 t squared. And 40 times 9, I have a 360. 360 t to the fourth. Oh, to the fifth. It's to the fourth. This is just 40 times 90 to the fourth. And then the other part of the foiling here will be 36t squared times 40t squared. Okay, so 36 times 40, I have 1440. T squared times t squared, t to the fourth. And last but not least, 36 times 9, which is 324. And that's t to the fourth. Wait a minute, t to the sixth. And then minus whatever we get from expanding the binomial here. Okay, so to square the binomial, instead of doing foiling, okay, let's use the binomial square formula. A plus b quantity squared equals a squared plus 2ab plus b squared. So what do we have? 40t quantity squared. That's another 1400 t squared. And check this out. With a minus in the front, that's going to cancel out with 1600. 1600. It's going to cancel out with the other one, which is great. And then plus 2 times 40 times 18, which is 1440 t to the fourth. Plus 18 squared, which is 324 t to the sixth. Everything under the radical. And divided by 40t squared plus 9t to the fourth. Okay, so let's cancel out terms. So instead of just distributing the negative and rewrite the whole thing, so I mean we can go with the negative sign. So we can cancel out the 1600 with the 1600, the 1440 with the 1440, and the 324 with the 324. All right. So it reduces. Okay. So that's gonna leave us with 360 t to the fourth over 40 t squared plus 9t to the fourth power. So that's an okay answer. However, we could simplify the numerator. Notice the numerator has a 36 as a perfect square factor times 10 and t to the fourth. And the whole thing divided by 40t squared plus 9t to the fourth. And well, the square root of 36, which is 6, and the square root of t to the fourth, that's a t squared, square root of 10, and that's over the square root of 40 t squared plus 9 t to the fourth. So those are the two components of the acceleration. This is the magnitude of the acceleration, or rather the projection of the acceleration in the normal direction, and the previous result, it's the one that goes along the tangential. Yes?
When you say normal component and tangential component, these are magnitudes and not vectors?
Yeah, these are magnitudes. Yeah, these are like the lengths of those shadows, of the shadow, the acceleration projects onto the normal vector and onto the tangent vector at a given, depending on the position. So we will get different values of t. So in this case, it's at different positions. All right.